Hello, it's Mr. Tarou, finishing up my notes for introducing scatter plots. Now, we are early, as I've said, and you're probably figuring out, early in the course of statistics, a course of which there's not a whole lot of background knowledge you have from other classes. So, unfortunately, if you watched 15 minutes of my notes a minute ago, and all of this is, again, just the concepts and to show you what to pay attention to, but we're still not going to actually do any problems, so I apologize for that, but there's just so much to pour out at you at once. And the next video will be how to actually create these graphs with your calculator. And actually I have one more graph in here I'm not going to be able to go over today either, but let's try and get this done. Take a pause and copy this. Okay, so we're going to start talking about how to measure the strength and direction of a linear relationship. All kinds of scatter plots can have all kinds of patterns in them, but since we're only in the intro to statistics, we can only deal with the linear ones. And how we're going to measure that linear relationship, and this is all about the definition and the properties of correlation. We're not going to see how to make that in this video, so if you need to know that, skip to another one where you see a picture of a calculator. Correlation R measures, that's a standard letter for correlation, at least in my textbook, measures the strength and direction of a linear relationship. Again, it has to be linear. Let's take a look at the formula before we look at these three bullets here. The formula for R, which your calculator or computer will do for you, is going to be R equals 1 over n minus 1 times the summation of x of I minus the mean of x over s of x times the y sub I minus the mean of y divided by the standard deviation of y. These little pieces, if you've been following along with me or hopefully working in your own stats book, look like z-score calculations. They look like standardized test statistic, and indeed they are. So we're going to convert all the measures of x and y into standard deviations away from the mean. So, keeping that in mind, you are standardizing the x and y values. So, R has no unit of measure. It's not in inches or feet or miles or grams. It has no unit of measure. It's been standardized out with the, well, as you know right now, a z-score process. You'll learn another test called a t-score much later. Changing the units of measure does not affect R. Well, if R does not have a unit of measure, then maybe, say, if you want to change the x-axis from, I don't know, for some reason, inches to feet, if you want to change that unit of measure, it's not going to affect R because R has no unit of measure. So if you convert one or the other axis's measures, unit of measure, it's not going to affect R. And it is also not affected by flipping the x and y value. In other words, if for some reason I felt like whatever was on the x-axis I now want to be on the y-axis, that's not going to change the strength measurement for the linear relationship. It's not going to change R. Now, on another screen, you're going to see that R ranges from -1 to +1. So that might look like if you have a scattering of points like this, where they're kind of very widely spread out, but maybe see a small downward trend of those points, that might have to be a correlation value of, like, say, -2. Whereas if I eliminate some of the randomness of these points, but yet still keep a downward slope, that might give you, oh, excuse me, that would be -0.2, excuse me, -1 to +1 for R. So if I narrow up the band of that downward trend, maybe that would give me an R value of, say, -0.8. If my pattern of points is positive, and I kept kind of a tight pattern here, maybe instead of -8, it's +8. Now, the +8, this is not a slope, so whether my segment looks like this, or even like this, if I keep the pattern of these points that gave me this R value, 0.8, the same, but somehow could rotate their slope, that would not affect R. R is not slope. It's strength and direction of a linear relationship. Now, if I were to rotate these points, though, and make the pattern completely horizontal, whether there was a band of points or even if they were perfectly horizontal, if I give you a pattern where one variable is changing and the other variable is not, there is no relationship, and that will yield you an R value of 0. Now your textbook will have a lot of examples of what scatterplot looks like and the correlation value that goes along with it, so you can estimate it. As far as actually calculating correlation, if you're using a graphing calculator, you will need to make a regression line, which you haven't heard me talk about yet. So again, this is all about just the definition and the properties of correlation. We're not going to calculate them because we're not going to do a calculator lab and make a regression line, which I haven't even introduced yet. Moving on. Woo! Got a lot to talk about. So, here are some other properties of correlation. What I just said, horizontal and vertical patterns will yield a correlation value of 0, even if that pattern is perfectly linear. Now I'm talking perfectly horizontal or perfectly vertical. One variable is changing and the other is not. R takes on values between -1 and +1. If the R values are exactly 1 or -1, that means that the points follow an exactly straight linear pattern. It's not about the slope, it's about the strength of that linear relationship. R is not resistant. If you back up a little bit, you'll see that the calculation of R uses the average again, and any calculation that uses average is not resistant. Remember, that is a measurement that is strongly affected by outliers. And correlation requires both variables to be quantitative. Well, as I talked about in the last video, scatter plots, this is a measurement that you take on scatter plots, are for quantitative data. Both the x and y axis have to be quantitative, so of course the same has to be true when you're working with a math formula and you're calculating R, or correlation. Alright, try not to use up all my 15 minutes. Bam! Or not run out of time. So, okay. Hopefully you go back and you pause that video so you can copy the notes. Now, one thing about finding correlation. Your calculator has no idea what those numbers represent when you put them in there, or the computer. So if you give a calculator or a computer some numbers, it's going to calculate those numbers whether or not it should, or it's appropriate. So you can have, well, let's read what I wrote. Curved scatter plots can yield correlation values close to 1 or -1, but since the calculation is only good for linear patterns, these results are misleading. Again, I'm talking about curved scatter plots. We cannot find strength of curved relationships. This is only intro to statistics. So you will have some questions in your textbook that maybe have a linear pattern, and you have maybe another graph that is, let's say, curved somehow. Or you may have a pattern that is somewhat linear, but has an outlier somewhere. Well, all of these may, and there will be a question in your book somewhere, where all of these values give the same R value. Maybe this R value is 0.7. Okay, well this is not linear, this is not linear, and this is not linear. I'll show you this when we do a calculator lab. But it is possible for very weird looking graphs to all give you the exact same correlation, but yet only one of them be linear. So, when you when you want to talk about correlation and the R value and the strength of a linear relationship, you must make a residual plot. Am I going to show you that today? Unfortunately, no. I'm trying to just give you a sort of outline of concepts you need to know. But a residual plot, at least in structure, is the original x values still on the x-axis and the residuals on the y-axis, the residuals of the y. And when you make a residual plot, I'll go more in depth later, but when you make a residual plot and you want to validate linearity, you do not want to see a pattern in that residual plot. Because what a residual plot will do when you see it being made is it magnifies any curvature that's in the graph. So if you try and run a straight line through a pattern that's curved, it's going to magnify that curvature. And so you might have a scatter plot that looks straight, but when you make that residual plot, it'll highlight that curve. So residual plots will verify that that is linear. And again, like me talking about normality and normality and normality, it might be a couple of videos before I finally define that for you. Actually, it'll be the next one where we use a calculator lab. Mean and standard deviations of x and y axis should be included in your description of a scatter plot, not just correlation. That's an incomplete question. You can't just say a scatter plot has a correlation of 0.7 and move on. Like, what else is there? Where does it start and end at? What's the slope like? Is it curved or straight? Or they're outliers? So don't just think that R is all the end all be all to describing a linear scatter plot. All right, one more little page. And if you take correlation and you square it, you get something called the coefficient of determination. Please do not change the wording of this definition. You can change the meaning of it, or just have it have it be complete nonsense very, very easily. So if I take the value of R and I square it, I get something called R squared, or coefficient of determination. It is the percent of variation in Y that is explained by the least squares regression line of Y on X. What the heck does that mean, or how are you supposed to interpret that? I gave you another little made-up scatter plot here. I did not put a vertical scale, I apologize, but it's just for the definition of R squared, or this determination. So I tracked mileage supposedly between the speeds of 30 and 70 and compared that to the miles per gallon that I was getting in a vehicle or a collection of vehicles. And we get this downward trend, which would make sense. The faster you drive, the more wind resistance and such, and your mileage will go down. Well, let's say I've collected this data, I've shown that it's linear, which again I'll show you in a computer lab or a calculator lab video a little later, and we get an R value of 0.8, and a R squared value then would be 0.64, because 0.8 squared is 0.64. This literally is squaring. It's not just a little footnote or notation. How are you supposed to interpret that 0.64 based on this definition? Well, your summary statement would be that 64% of the variation in miles per gallon, the variation in Y, is explained by your speed between 30 and 70. 64% of variation in Y is explained by the speed you're traveling between 30 and 70 miles per gallon. You know, what could the other 36% be? I don't know. The weight of the car, the air in the tires, the speed of the wind at that particular time you were driving within that speed. That's not really anything that we have to come up with or explain, but we do have to know the definition of R. We do have to make a good summary statement based on that definition. Please do not change the wording. Just use it as it stands, and there you go. The next time you hear me talk about regression lines or scatter plots, we will be drawing regression lines through those, so we'll need another set of notes for that, and then a calculator lab to finally figure out how to get all of these numbers that we want to use later on. Bam! Have a great day.